Okay. So, we are looking at the different efficiency and performance parameters, and we have looked at all this propulsion efficiency, thermal efficiency, propeller efficiency, and the overall efficiency for turbojet. Now, the same thing we are going to look at how it varies for turbofan engine. Now, for turbofan we are going to derive those similar expression so the parameters can be for turbofan. Okay. So, here as we recall, the engine has two sections, just getting it and just to recall that. So, then you have compressor, then finally it goes through that. So, these are hot exhaust, these are cold exhaust, this is U. So, there are two contributing factors, one is the cold thrust, other one is the hot thrust. So, they contribute to each other, and they both of them actually the total thrust component of the cold and the hot. So, here the thermal efficiency could be like m dot E h into U E h square by 2 plus m dot E c square by 2 minus U square by 2. So, where m dot A is m dot A c plus m dot A h, and we have m dot E h equals to m dot A h plus m dot A f, and m dot A c is m dot E c. So, f would be m dot f by m dot A h. So, we can just write this one 1 plus f square plus m dot A c by m dot A h minus 1 plus U square 2 f q r. Now, similarly, the propulsion efficiency, which is T u by m dot E h U h square by 2 plus square by 2 minus m dot A u square by 2, which we can again simplify like 1 plus f minus u plus A c by m dot A h minus u into u divided by u square by 2 plus A c by m dot A h minus 1 plus m dot A c by m dot. So, we can have the propulsion efficiency and thermal efficiency in this fashion. Now, we can look at the curve like how, let us say, if we draw it with the airspeed and this side propulsive efficiency, then we have curve like so. Curve goes like that. This is pure turbojet. Then we have this, then we have this, then we can have this is turbo prop, this is low bypass, this is high bypass turbofan. So, that gives you an idea how propulsion efficiency with the airspeed that varies. So, if you take an lower airspeed, then you can see that is what we have been always talking, that at the low speed application turbo propeller engine is quite effective. You can see the propulsive efficiency is the maximum, but as we increase the airspeed this side, then obviously the propulsion efficiency of the turboprop engine drops, but at the same time we have the turbofan and turbojets, their efficiency goes up, propulsion efficiency. So, another curve which may be interesting to just note, again this is with airspeed and this is propulsion efficiency. So, this is for like, and this is for propeller fan, and this is contra rotating fan. So, even their propulsive efficiency can be compared, how these things actually varies. Now, what we can look at is the with this kind of efficiency and other parameters. So, we can really go to some particular trend. So, these are the some of the pictures which are give you an idea like how this different kind of engines and what is there. So, let us look at this first picture. So, this is the core thermal efficiency versus propulsion into transmission efficiency, and you see this the old Whittle engine where they belong, and this side is the overall efficiency, and this also SFC. So, this is where our turbojet, then low bypass ratio turbofan, then current bypass ratio turbofans which are there. Then we have future trend, how things are going to be advanced in this direction. And other one which is there is the depending on the bypass ratio, this is the different factors of the bypass ratio, and this is the fuel consumption rate or TSFC, thrust specific fuel consumption. This is where turbojet lies, you see quite top, then turbofan with bypass ratio 1, then low bypass ratio, you have medium bypass ratio, then high bypass ratio, turbopropeller, and these are the different example of all these different category of engines where they belong and how their performance parameter, which as I just tried to draw schematically. Now, the another curve which would be interesting to see is the specific thrust characteristics, where again this is the aircraft Mach number, and you can see how the trend looks like. The trend is, you have turboprop here, then you go to high bypass ratio turbofan, this is low bypass ratio turbofan, and that is where that turbojet belongs to, and that is the one which finally takes to the TSFC characteristics, that is your specific fuel consumption rate with the aircraft Mach number. Again this bottom curve is turboprop, then you have high bypass ratio turbofan, then you have low bypass ratio turbofan, how that is changing, and in between there is a small deviation for the turboprop, which is the conventional propeller engine, and this is where the turbojet. So, the interesting thing to note here, let us say given a Mach number, if it is low subsonic range, let us say we come here, the TSFC is quite high for turbojet and then low bypass ratio and turbofan. But when I go to high Mach number, then you can see this is what, that is why low speed application turboprop is preferred, and high speed application bypass ratio turbofan, these are preferred, and at the same time the other curves also kicks in. Now, that will give you some idea about how these trends and are. Now, moving forward, the important one is that we look at the takeoff thrust. Now, this is another important factors that actually affects the performance. So, this is, as I said, one of the most important characteristics, one of the most important characteristics of a gas turbine engine or of a turbine engine installed in aircraft. So, it can provide static or low speed thrust, ramjet cannot. So, this takeoff thrust is very important, because this can be only produced when we have this combination of compressor and turbine and such that, but it can provide static or low speed thrust. So, ramjet engine cannot do that. So, that is important restriction for ramjet engine. Now, any aircraft can take off under its own power. So, that is which is essential requirement, and at the same time during takeoff aircraft needs the max power during takeoff. So, also this is important that takeoff thrust is going to be the maximum thrust, because this required during takeoff, and the takeoff usually happens at the sea level, where air density is also maximum at ground level, and that leads to higher drag, because this is proportional to density. So, the aircraft has to also overcome frictional forces on the wheel. So, it has to overcome frictional forces on wheel, also full load with maximum fuel. So, that means the load is full load with max fuel. That means while the aircraft is taking off, that time you have the maximum payload carrying, including the fuel weight, which is also maximum. So, this is an very important design parameter, because this is the max thrust generated by an engine, and that is what required during takeoff. Now, how that makes things different or how it affect, let us see. It is simple. We will start with the, let us say, thrust equation. So, that is T equals to m dot A minus U plus P A E. Now, what happens at startup, U goes to 0 or U is very smaller than U e. So, which will lead to m would be quite small, and that means P e, what is there, that should be P a, that means the atmospheric condition. So, with these conditions, one can write the thrust which is going to be during takeoff. It is equals to m dot A into 1 plus F U E, and always we keep on saying so far, rather instead that in general F is very small, but one can always say why, or one can look at it just to justify that statement which we have been always talking, that fuel air ratio would be always less. Let us say any hydrocarbon fuel you take, let us take the simple one, typically methane. So, what happens, just look at the methyl combustion. So, this is 2O2 plus N2, which will lead to CO2 H2 plus 7 N2. So, that is sort of a balanced equation. Then here fuel is 16, and if you look at this year, which is this is 7 into 28 plus this is 2 into 32, this would be roughly 260. Now, the fuel air ratio would be 16 by 260, which is 0.06, and that is what we always say. In general, these engines, the fuel air ratio is quite small. And just an example, now you can take the other fuels, like all these jet fuels or things are all hydrocarbon fuels, which are of the similar category, and you can have this. Now, let us coming back to this takeoff thrust. If, since F is small, we can write takeoff thrust is m dot A into U A, which means T O by m dot A is U E, which is the static thrust per unit mass. Okay. Now, this static thrust per unit mass, this guy is directly proportional to exit or exhaust velocity. Okay. That is what we can see, but it would be interesting to also look at for a given flow rate how does thrust depend on exhaust velocity. So, that would give us a important aspect, or this answer also, this will also, or this answer to this question also shed some light that one of the major differences between turbojets and turbofan, etc. So, this plays a significant role in the choice of propulsion system for specific application. That means, this guy plays a significant role in the choice of propulsion system for a specific application. Let us see how that happens. So, we have already derived the relationship for the thermal efficiency, and the thermal efficiency is 1 plus F minus U square by 2 by F into Q r. Now, for static engine, U goes to 0 or U is very smaller than U e, and at the same time we have F is smaller than 1. Then we can write this thermal efficiency as U square by 2 F Q r, which is equivalent to writing m a U square to m dot Q r. Now, from here what we get, that m dot A to m dot F eta thermal efficiency Q r divided by U e square, and also we know thrust is m dot A, that takeoff thrust that we have got, m dot A, which is the takeoff thrust essentially U e. So, we can write this is 2 m dot F eta thermal by Q r into U e. So, this is what a important finding. So, this one can say this thrust is here, we mean to say that takeoff thrust here. So, this is here, it is takeoff thrust. Now, what we can see for a given fuel flow rate and thermal efficiency, this takeoff thrust would be inversely proportional to UE, and we have seen thrust is also proportional to m dot A. So, which clearly says that for a given rate of energy consumption, the takeoff thrust can be increased by accelerating a longer mass flow of air to a smaller exit velocity. So, this is very important that for a given rate of energy consumption, the takeoff thrust can be increased by accelerating a longer mass flow rate of air to a smaller exit velocity. That means, if you club these two clauses together, either we can increase m dot A. Once we do that, takeoff thrust could be increased, but or we can so with the larger mass flow rate and smaller exit velocity. That means, when the engine is starting off, during taking off the aircraft, this guy may be small, but with larger mass flow rate it can be increased, the takeoff thrust can be higher. And m dot A for turbofans are greater than that of turbojet. So, now you can see why these recent developments is a pretty much a common choice of using turbofan engines, but this can provide higher takeoff thrust. But UE is higher, or it's much higher for turbojet. Now, combining this, one can think about this takeoff thrust for turbofan and turboprop are much higher, that is compared to turbojet. So, that is why you can see why, as I said, turbofan engines are preferred. So, they are widely used in big civilian airplanes, because they provide higher takeoff thrust to take off with larger weight, and that is one of the primary reason why these days all the development which are one can see, even when you have seen the recent development and the kind of engines what we have discussed during the introduction or introductory lecture, this turbofan is more and more popular, but with a different blends of different blends of bypass ratio. Sometimes it is a low bypass ratio, sometimes it is a high bypass ratio, it depends on the application, depends on the user choice. So, that is how the development is going on, and turbofan is more and more popular or gaining popularity, or rather used in the recent developments. So, we will look at the other aspect in the next lecture.